Hey, what's going on, guys? In this video we are going to see how to calculate intensity of interference pattern that is inside of the central maximum of diffraction pattern. So here we have diffraction pattern that is given by blue color and interference pattern is given by this red color, and we are going to find the intensity at the location that is 0.22 centimeter away from this central maximum of this interference pattern, right? Now to calculate this intensity anywhere, we have to use this equation, that's I is equal to I naught times sine and phi over 2 and these things, right? So let's try intensity at any location that is given by I. I naught is basically intensity of single beam, and that is multiplied by sine and phi. Here phi is phase angle of interference pattern and beta is phase angle of diffraction pattern. And for phase angle we use this equation, right? This is phi is equal to x distance over lambda times 2 phi. So for diffraction and interference is going to be a little bit different. We are going to see that. So here let's see what are the things we need in order to calculate this one. So n is number of slits. So here we have 2 slits, so we already know that. We have to calculate this phase angle of this interference pattern and also phase angle of this diffraction pattern. Now let's start with interference pattern, that is phi is equal to x distance. Okay, for interference pattern the x distance is going to be the distance between these 2 slits, that is this d, times sine theta. And the difference between interference and diffraction pattern is, here we multiply d by sine theta. For diffraction pattern we are going to multiply this slit width, that is a times sine theta over lambda times 2 phi. We have to put 2 phi, and here also we have to put 2 phi. And if you look at this equation, here we have to have phi by 2 in angle, right? We need both of them in angle because we have sine phi by 2, sine phi by 2. So we have to have, so let's to make this one clear, let's write this one. This is interference and this is diffraction, right? So for interference we have to have this one in angle, but for diffraction we have to have this one in radians and also in angle because we need both of them. In the top we have angle, but in the bottom we have to have this one in radians. So let's calculate this one in radians, but this one we can directly calculate this one in angle. So what we have to do is, instead of this 2 phi, we can simply multiply this one by 360 degree. So in that way we don't have to change anything, right? So if we calculate 360 degree, that's going to give us the straight answer. So here we know that so all we have to do is just plug the values. Now let's go ahead and plug it. So first we have d, that is 0.55 millimeter, and if we expand this one, that's going to be 0.0005 meter times then sine theta times this one, right? Now sine theta, instead of sine theta we can put tan theta because we are dealing with very small angle. So tan theta we can put instead of sine theta, and tan theta is going to be opposite over adjacent. So opposite is the total distance over adjacent. So we have adjacent length, that is 2 meter. We need to have an opposite distance. Okay, so we have to make up a number. So let's say this. Oh, okay, so we have only dealing with this distance, right? This y is equal to 0.22 meter. So this is the one we are looking for, right? So this, if we consider this theta, this height is 0.22. so if we write this one, so let's create the equation first. So opposite over adjacent is going to be y over L. So now we can go ahead and plug it right here, right? So instead of this one, so let's let's write the equation in better way, then we can plug it. So d sine theta over lambda can be written as d tan theta over lambda times 360, because for a small angle sin theta can be equal to tan theta. So since we are dealing with small angles right here, we can equate like this, right? And then tan theta is opposite over adjacent, so this is going to be dy, opposite is y, right? And lambda and adjacent is L, so lambda L times 360. Now we can go ahead and plug the values. So d is 0. If this is in millimeter, so this is going to be 0.5 10 to the power of minus 3, and y is 0.22 centimeter, so this is going to be 0.22 times 10 to the power minus 2 meter, and also lambda is 500 nanometer, so this is going to be 500 times 10 to the power of minus 9 meter, and the length is 2 meters, so we just multiply by 2 times 360 degree, and if you solve this one you should get 396 degree. In other way you can just say 360 plus 36 is 396 degrees, right? So we can just say 36 degree. So here we found out the phase angle of the interference pattern. Now we have to find the phase angle of the diffraction pattern. Now to find this one we have to use this equation. Again we can do the same thing right here. Instead of a sin theta phi, we can write a tan theta over, actually tan theta over lambda. So tan theta we know that opposite over adjacent, so we can write this equation as a y over lambda L. Same approach like this, right? Now if you calculate this one, let's plug the values. A is slit width, that is 0.1 times 10 to the power minus 3, and y is 0.22 centimeter, so 0.22 times 10 to the power minus 2, and then we have lambda, that is 500 times 10 to the power minus 9, and length is 2, and also we have to multiply this one by 2.5, and if you calculate this one you should get, this one should be equal to 0.445, and if you convert this one into angle, that's going to be 79.2 degree. Now we have these two phase angles. Now we have diffraction phase angle, and also we have interference phase angle. Now all you have to do is just plug it in this equation. You know what, let's get rid of some part, we need space, right? So we just need this value. I get rid of this part so we can write the final equation. Okay, so we have this phi is equal to this one. Now let's go ahead and plug the values. I is equal to I naught. I naught is intensity of single beam, so we keep it as I naught, and sine time number of slit, we have 2 slits, so we put 2 right here, and we found out this one phi is 36 degree, so 36 degree divided by sine, so here we have to divide this one by 2, so we just put a 2 right here, and then in the bottom we have sine 36 divided by 2, and that's it for this one. And let's continue other side. So this time square. After that sine beta over 2, beta value we found out that is 79.2 degrees, so this is going to be 79.2 divided by 2 over beta by 2 is going to be this phi value divided by 2, 0.445 divided by 2 square, and that's it. After that you will get, if you calculate this one, you will get I naught times 3.618, and if you calculate this part, that's going to give you 0.8506, and finally the total value you will get is actually 3.077 I naught. So that's going to be our final answer. So the intensity at this location is going to be 3.077 I naught, and that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.